In the last couple of lectures, we investigated diagonalizability. We saw what characteristic polynomials are, what the determinants are, and the characteristic polynomial, which is the solution of a determinant equation. And we also saw the necessary and sufficient condition for a square matrix to be diagonalizable. And we express this through the arithmetic and geometric multiplicities of the characteristic polynomial. So the algebraic multiplicity was a property of the characteristic polynomial of the matrix, and the geometric multiplicity is basically the dimension of the corresponding eigenspaces. And we saw that if these two are equal, then only then the matrix is diagonalizable. So in the next couple of lectures, we'll investigate another condition for diagonalizability, but not in terms of the characteristic polynomial and the eigenspaces themselves, but in terms of polynomials. So the next couple of lectures will be much more algebraic, but we'll see some very nice properties along the way. In this lecture and the next, we'll go through the Cayley Hamilton theorem. So this is something that's familiar to all of you. So the Cayley Hamilton theorem says that every square matrix satisfies its characteristic equation. Now note that the characteristic equation is basically it's basically a determinant equation. It's just a determinant of lambda I minus a equal to 0. And at this point, it's quite surprising that that every square matrix must necessarily satisfy this polynomial equation. Right? So recall the characteristic equation is determinant of lambda I minus a equal to 0, where lambda is the variable in question. So this is some polynomial in the variable lambda, and what the Cayley Hamilton theorem says is that f of a is equal to 0. So this matrix polynomial evaluates to 0. And this is a very nice result, and we'll see more of this later. So in general, any polynomial p of x, it satisfies the property that p of a is equal to 0. Given a matrix A, if p of a equal to 0, then that particular polynomial p of x is what we call an annihilating polynomial for A. And it's annihilating because it sort of kills the matrix, right? So if you take a polynomial function of that particular matrix, then it gets killed to 0. Right? And we'll try to address in this lecture and the next what is the smallest degree polynomial p of x such that p of a equal to 0. So what is the smallest degree of an annihilating polynomial, right? And just to make sure, so note that if p of a is equal to 0, then alpha times p of a is also equal to 0 for a constant, for any scalar alpha, right? And to avoid kind of this ambiguity regarding the sort of smallest polynomial, just to make sure that the smallest polynomial is unique, we'll add an additional constraint on the polynomial. So we'll add the property that so we want to ask what is the smallest degree monic polynomial such that p of a equal to 0. So what is a monic polynomial? A monic polynomial is one which is of the form x to the m plus a m minus 1 x m minus 1 and so on plus a0, right? So basically the coefficient of the monomial with the highest power, that is x to the m, the coefficient of x to the m is always equal to 1. So that's called a monic polynomial, and this ensures that the polynomial is unique, because any scalar multiple of the monic polynomial scaling by any other factor other than 1 gives you a non-monic polynomial, right? So in that sense, the polynomial is unique for a given degree, right? and therefore, and of course, so it doesn't, so at this point it doesn't really mean that the polynomial is unique. So there could be two different polynomials of the same degree, two monic polynomials of the same degree, which could evaluate to 0 at this point, at this particular point, right? So we'll say that, so when I say what is the smallest polynomial, we'll ask for the following conditions. So we want p of a to be equal to 0, and we also want that p of x is monic, right? And this is a minimal polynomial in the sense that if q of x equal to, if q of x is another polynomial such that q of a is equal to 0, then it must necessarily mean that q does not divide p. So any other polynomial which is also an annihilating polynomial cannot divide p. Okay, so these are the conditions that we will ask for. So this is what I mean by a smallest degree monic polynomial, and such a polynomial is what we'll call a minimal polynomial. So minimal polynomial is any polynomial. The minimal polynomial of a is a polynomial which satisfies p of a equal to 0. P of x must be monic, and if you have any other annihilating polynomial of a, then it cannot divide p. Okay, so our goal is to find what is the minimal polynomial of a. And why are we interested in the minimal polynomial at all? It turns out that if an alternative characterization of the diagonalizability of matrices can be expressed in terms of minimal polynomials, right? So for example, here's a simple exercise, right? So take any matrix which is diagonalizable. Here's an exercise for you. Take any matrix A which is diagonalizable and find the characteristic polynomial. Okay, let's take, for example, let's say 1 1 2 2. Okay, find the characteristic polynomial of this. You'll see that the characteristic polynomial factorizes into, so it will be x minus a1 times x minus a2. So this will be a polynomial which does not have any repeated roots. Okay, so the roots would be distinct. Now take this matrix. We've seen in our previous discussions that this matrix is not diagonalizable. Now it will turn out that this has a characteristic polynomial which is equal to x minus 1 the whole squared. So x minus 1 the whole squared is the characteristic polynomial corresponding to this particular matrix A. Okay, and it turns out that this is also the minimal polynomial for A. So it will turn out that a matrix is diagonalizable if and only if the minimal polynomial does not have any repeated roots. Okay, so as long as all the roots of the minimal polynomial are distinct, the matrix is diagonalizable. But anyway, we'll get to that much later. But first, let us ask the question: what is the degree of the minimal polynomial? But even before that, can we always find a minimal polynomial? Right? Is there a finite m such that there exists a polynomial of degree m which is annihilating A? right? And a very loose bound on the degree of the polynomial can be found in the following way. Now recall that if you have a matrix A which is n by n, right? I claim the following. I claim that the matrices I, A square, A cube, so on, A to the n squared. Now these matrices are linearly dependent in the sense that I can always find a non-zero linear combination alpha 0, alpha 1 up to alpha n squared, such that alpha 0 I plus alpha 1 A and so on up to alpha n squared A raised to n squared is equal to the zero matrix. I wanted to pause this video and think about why this is the case. Okay, so note that A is an n by n matrix, and the set of all n by n matrices forms a vector space of degree n squared, right? And since the dimension of this vector space of n by n matrices has dimension n squared, any set of n square plus 1 vectors must necessarily be linearly independent. Otherwise, you would be able to find a basis or a linearly independent set of size n squared plus 1, which is impossible because the basis is necessarily the maximally linearly independent set, right? So therefore, this tells us that the degree of the minimal polynomial must obviously be less than or equal to n squared. In fact, as we go on towards the end of this lecture, we'll see that it's not just less than or equal to n squared, it must be less than or equal to n. And this is what we get using the Cayley Hamilton theorem. Okay, so now that we know we have an upper bound on the size of the minimal, on the degree of the minimal polynomial, let's ask the following question. What are the roots of the minimal polynomial? So we're trying to successively characterize the properties of the minimal polynomial of any n by n matrix A. So what are the roots of the minimal polynomial of A? Now here's a very nice fact which is not obvious at all. The roots of the minimal polynomial of A are precisely the eigenvalues of A. So every eigenvalue of A is a root of the minimal polynomial, and every root of the minimal polynomial is an eigenvalue of A. So recall, the minimal polynomial is the smallest degree polynomial which annihilates A. Right? So it's a polynomial P of A, P of X, such that P of A is equal to 0. Now every annihilating polynomial, so an annihilating polynomial can have arbitrary roots. In particular, if P and Q are two annihilating polynomials, so if P is an annihilating polynomial, so P of A equal to 0, then and Q is any other polynomial, then Q times P, if you multiply the two polynomials, then Q times P of A is also equal to 0. That is obvious. And if P and Q are two different annihilating polynomials of A, then P plus Q of A is also equal to 0. So it turns out that the set of all annihilating polynomials form what is called an ideal. So it's an abstraction or a more general version of a field, in the sense that it satisfies fewer properties than what a field is supposed to satisfy. But the set of all annihilating polynomials of a matrix A form what is called an ideal. So that's an algebraic term. But what is interesting here is that the minimal polynomial of A, we can exactly characterize them with the roots of the minimal polynomial of A, and it turns out that all of them and that these are precisely the eigenvalues of the matrix A. So let's prove this particular statement. So note that we have to prove, in fact, we have to prove two statements. One, every root of the minimal polynomial is an eigenvalue, right? And the second property is that every eigenvalue of the matrix A is a root of the minimal polynomial. So these are necessary and sufficient conditions for the roots of a minimal polynomial. So it should necessarily be an eigenvalue, and if it is an eigenvalue, it's sufficient for it to be a root of the minimal polynomial. Right? So let's try to prove statement 1. Right? We want to show that every root of the minimal polynomial is an eigenvalue. So let's say that P of x is the minimal polynomial for the matrix A, right? And let's assume that C is a root of the minimal polynomial, right? So C, for now we'll just assume that we're dealing with complex vector spaces. So the constant C is a root of the minimal polynomial. So what does this mean? We can write P of x. So since C is a root, we can write P of x equal to x minus C times Q of x. So assuming that P of x has degree m, Q of x, so P of x has degree m, Q of x will have degree m minus 1, right? So Q of x is some polynomial, and Q of x has degree m minus 1. P of x is the minimal polynomial of A, right? So now I claim the following. So there should exist a vector u in C to the n such that Q of A times u, so let's call this v, this is not equal to 0. So there should exist some vector u which is not killed by Q of A. I want you to pause the video and think about why this particular statement is true. Okay, so this should happen because Q of x cannot be an annihilating polynomial for A, right? Because if Q of x is an annihilating polynomial, so if suppose that for all vectors u, Q of A times u equal to 0, then it must necessarily mean that Q of A is equal to the 0 matrix. If it is a non-zero matrix, then that cannot happen, right? It cannot happen for all vectors u. But if Q of A equal to 0, then it must mean that Q of x is annihilating, which cannot happen because it has degree less than P of x, and P of x is the minimal polynomial, right? So it must mean that the vector v, which is Q of A times u, is not equal to 0, right? So let's look at P of A, which is x, A minus Ci. So P of A is A minus C times I times Q of A, right? So if I multiply both, if I multiply both these sides by the vector u, then I get A minus C times I times v, because we assume that Q of A times u equal to v, and v is a non-zero vector, right? But what is the left hand side? Since P of x is the minimal polynomial, P of A is the 0 matrix, and therefore P of A times u is 0, right? So 0 equal to A minus Ci times v. So this implies that A times v is equal to C times v, right? And this can happen only if C is an eigenvalue of A. By definition, C is an eigenvalue of A, right? And v is a non-zero vector, remember that. So every root of the minimal polynomial must necessarily be an eigenvalue of A. So once again, we started with the minimal polynomial, and we assume that some number C is a root of the minimal polynomial. There's no other assumption except that C is a root of P. Right? So we can factorize P of x as x minus C times Q of x. And Q of x cannot be an annihilating polynomial, so we can find a u such that x minus C times Q of A times u, so such that Q of A times u is non-zero, and this leads us to the fact that C should be an eigenvalue of A. Okay, and really the point where we used the fact that and this can happen only if P of x is the minimal polynomial, not an arbitrary annihilating polynomial, because we needed the fact that P is an annihilating polynomial, but Q cannot be an annihilating polynomial. Right? Okay. So now that's fine. Now what we want to show is that every eigenvalue of A is necessarily a root. Right? So we have P of x so P of x. So let's suppose that P of x is the minimal polynomial of A. Right? What we want to show is that P of, so if lambda is an eigenvalue of A, then we must show that P of lambda equal to 0. Right? And this is very straightforward, because if we take P of A times u, so corresponding to lambda we have an eigenvalue u, right? We have an eigenvector u corresponding to the so let's suppose that u is an eigenvector corresponding to the eigenvalue lambda, right? So P of A times u is equal to P of lambda times the vector u, right? And u is a non-zero vector. So u is a non-zero vector, and since so lambda is the eigenvalue corresponding to the eigenvector u, and P of lambda times u is equal to P of A times u, right? So since A is an annihilating polynomial for A, P of A is equal to 0. So the left hand side is equal to 0. So this is equal to P of lambda times u, and u is a non-zero vector, and this can happen only if P of lambda equal to 0, right? So therefore every eigenvalue lambda of A is necessarily a root of the annihilating of the minimal polynomial. In fact, every eigenvalue is always a root of any annihilating polynomial of A, right? Okay, so let's quickly go through this again. What did we do? We basically used the property that if P is any polynomial, then P of A times u, and u is, so if P is any polynomial and u is an eigenvector with corresponding eigenvalue lambda, then P of A times u equal to P of lambda times u. So remember that the left hand side, P of A is a matrix polynomial, whereas P of lambda is basically an evaluation of P of x at x equal to lambda, right? So it's a scalar. P of lambda is a scalar, whereas P of A is a matrix, right? So P of A times u is equal to P of lambda times u. Since P of A is an annihilating polynomial of the matrix A, P of A times U obviously has to be the 0 vector, whereas the right hand side is P of lambda times U. Since U is an eigenvector which is non-zero, we must necessarily have that P of lambda equal to 0, which implies that lambda is a root of P. Okay. So in effect, we've proved that the roots of the minimal polynomial are precisely the eigenvalues of A. So this means that every root of the minimal polynomial is an eigenvalue of A, and every eigenvalue is a root of not just the minimal polynomial but any annihilating polynomial of A. Right? So one thing that must be noted over here is that the characteristic polynomial of a matrix is not necessarily equal to the minimal polynomial of a matrix. So here is an example. Consider this particular matrix A, 5 minus 6 minus 6 minus 1 4 2 3 minus 6 minus 4. So I want you to pause this video and compute the characteristic polynomial of A. Okay. So once you've computed the characteristic polynomial, I want you to verify that this polynomial P of x, which is equal to x minus 1 times x minus 2, this is an annihilating polynomial of A. In fact, it turns out to be the minimal polynomial for A. So P of A, which is A minus I times A minus 2I. So verify that this is equal to the 0 matrix. Right. So the characteristic polynomial of A, which will turn out to be a polynomial of degree 3, is not the same as the minimal polynomial, which turns out to be a polynomial of degree 2. I've not proved that P of x is the minimal polynomial of A. All that I've shown is that this is an annihilating polynomial for A. Right? And in fact, this does turn out to be the minimal polynomial of A because of the property that 1 and 2 are the eigenvalues of x. Of A, 1 and 2 are the eigenvalues of A, and therefore this is the smallest polynomial which contains both eigenvalues, and it is also an annihilating polynomial. Okay. So if the matrix A is diagonalizable, then we can precisely say what the minimal polynomial must be. So if A is diagonalizable, and suppose that the characteristic polynomial for A has the following form: x minus lambda 1 raised to d1, x minus lambda 2 raised to d2, and so on, x minus lambda k raised to dk. So suppose that for a matrix A, this corresponding f of x is the characteristic polynomial of A. Then the minimal polynomial for this matrix A, assuming that it is diagonalizable, turns out to be x minus lambda 1 times x minus lambda 2, x minus lambda k. So this will be the minimal polynomial for A. Okay. So why is this true? So firstly, note that this polynomial over here, this P of A must divide the minimal polynomial. Why is this true? Yeah, so this is true because lambda 1, lambda 2 up to lambda k are the eigenvalues of A, and each of these is a root of the minimal polynomial of A. We've just shown that, right? And this is the smallest degree polynomial which has all the roots being equal to the eigenvalues. So P of A must divide the minimal polynomial, but it's not necessarily so we don't know if it's annihilating or not. Second claim is that P of A annihilates A. Right? So P of A equal to the zero matrix. So I want you to pause this video and try to prove this yourself. Alright, so proving this requires you to make the following observation. If P of A equal to 0, then one way to prove this is that for all u in Rn in Cn, P of A times u equal to the zero vector. So if this happens, then P of A must necessarily be equal to the zero matrix, right? And how can we prove this? So note that every u, so if A is diagonalizable, then we can have a basis of eigenvectors. Let's call v1, v2 up to vn to be the eigenvectors of A. So you can write any u as summation I going from 1 through n of alpha I vi, right? So this times P of A, but this is summation I going from 1 to n of alpha I P of A times vi. But P of A times vi, since vi is our eigenvectors, so this is summation over all I, alpha I, P of lambda I times vi, right? But what is P of lambda I? P of lambda I is equal to 0 because lambda I, the lambda i's are roots of the polynomial P. So this is equal to 0, right? Okay, so if A is diagonalizable, then we know exactly what the minimal polynomial must be. The degree of the minimal polynomial is k, where k is the number of distinct roots of the characteristic polynomial, or k is the number of distinct eigenvalues of A. Okay, but what if it is not diagonalizable? If it is not diagonalizable, then it will turn out that the roots, so it turns out that the minimal polynomial will have repeated roots, and we can in fact show later that if the matrix has repeated roots, if the minimal polynomial has repeated roots, then it is not diagonalizable. Right? So clearly, if the matrix is diagonalizable, then the minimal polynomial will not have repeated roots, right? But the fact that this is sufficient is still a non-trivial fact. Okay. The goal of the next lecture will be to prove the so-called Cayley Hamilton theorem, which says that if f of x is the characteristic polynomial of A, then f of A is equal to 0. It's equal to the zero matrix. So this will tell us that the minimal polynomial of A must have degree less than or equal to n for any matrix A. So we've already seen that, so at least for a diagonalizable matrix A, it is clear that f of A is equal to 0, because we've shown that P of A equal to 0. So P of A equal to 0, which must necessarily imply that f of A is also equal to 0. So for diagonalizable matrices A, every matrix satisfies its own characteristic equation. Every diagonalizable matrix satisfies its own characteristic equation. The extension to non-diagonalizable matrices is the non-trivial step, and that is what we will prove next.